Hi, welcome to the fourth Masterclass for Kaizen Neuromap this summer, 2021. And we're going to talk about hemispheric differences, and that will be a lengthy topic to go over. There you can see the left and right hemisphere, left in blue, right's in purple. And below it is the brainstem and cerebellum, and so forth. Okay, here we can do a very simple task to find out if you're typically organized. Typical organization is when you have your left hemisphere as the dominant hemisphere. In essence, mostly you're speaking out of your left hemisphere. The right hemisphere handles things like face and emotional recognition. So what we do to figure out a quick way to understand one's hemispheric organization, have them look at this kind of what's called a chimera face, and look at one, let's look at the other one, which one is happier? And if you see that the left one is happier, that would be you have the reverse organization. Your dominant hemisphere is your right hemisphere. If you see the one on the right here is the happier one, well, that is the typical organization, which you see in most people, 95% of the people. But people who are seeking neurotherapy often, we do see some more reverse more often because they have more issues. And that's why they're seeking neurotherapy. So why does this work? Well, the visual field is such that everything to the left of the center point goes to your right hemisphere. So this green colored part, and everything to the right of the center, if you're looking at the center, so you're looking here in the center, everything to the right goes to your left hemisphere. Well, one great distinction of the two hemispheres, and I'm going to use left as dominant hemisphere throughout this talk, though again, some people will be reversed, so the dominant hemisphere would be right, but just using the typical, left is dominant. The left is categorical. It collapses sensory information to core representations. What's the category? Looking at some animal, is that a cat? Yes, it shows catness. The right is configural. It maintains the details. It doesn't collapse. It's experiential, and it maintains the experience. And in fact, when you talk about like savants, autistic savants in particular, often they are very right-brained, maintaining all these details. And emotional perception from face recognition or emotional perception or emotional recognition in a face is a configural process. It's not really categorical. So whichever, the right hemisphere should be the one processing it. So when you're looking at this is going to the right hemisphere, the sad face. This one's going over here to the happy face. This should be viewed happier. And all we know a lot about this because it's one classic paper. I love papers that are not peer reviewed because peers can get in the way often. They're colleague reviewed, I like to say. Sometimes they're not peers to the paper. And this is a non-peer reviewed. A lot of things we know about frequency analysis was done in a white paper by Tukey in 1940s I think for the Navy. And it was not peer reviewed, and so much came out of that. Don't let the peers get in the way of the concepts. And this is about individuals who have intractable epilepsy to the point that they're going to try to remove where they think the seizure focus is. Seizure focus itself may be more myth than reality. But in these cases, what they would do is looking at those who have seizures, they don't want to remove the part of the hemisphere, the part that is involved in speech, because then it's going to damage the person's quality of life more than just letting the seizures exist. And so they do what's called a water test. And the water test is you sedate using the carotid one hemisphere at a time. And you ask them to answer questions, count back by 10, look at pictures. Is that a bird? Is that a spoon or whatever? And what they found out, what Brenda Milner, who I encountered in my lab years ago, and Rasmussen, who I have no clue who that is, what they found out is that in right-handed individuals, almost all of them spoke out of the left hemisphere. That was the expressive speech. 4% didn't. When they look at water tests or equivalent like fMRI involvement in more normal brains, non-epileptic brains, it gets to about right-handed usually about 100%. Left-handers look often like a right hand, about 70%. This is the canonical findings. You'll see in papers written, they'll still use these numbers because 70% of the left-handers spoke from the right hemisphere. I mean, from the left hemisphere, I should say, sorry. And the one thing you find out is there are actually two forms of speech. You couldn't really pick this up from just talking to people. There's the form of spontaneous speech, just speaking, fluency and so forth, speaking, and then naming. Naming speech is done by a different hub or network, I should say, a different network in your head. And they found that in left-handers that some could do naming in one hemisphere and spontaneous in the other. And then you have this reversal. And the whole interesting thing, which we're going to get into, is handedness. Is how do you get these reversals? What's going on in these left-handers? How do you become left-handed? Given that we have such a dominance of right-handedness in our species. Okay, so we're going to look at hemispheric differences. So these are on the surface. So, all right. I love this little picture here. Now, this is one of the slides I've shown, oh my goodness, for 20 years at least now, of about paw preferences. And the let's see, let me make this, why is this cutting away? Maybe I change my taskbar here, get it to hide. Oh, it's gonna take a moment, sorry about that. At least this is, see if I can find it. I want to make it, because I don't want that bottom being cut off. So automatically hide the taskbar. There we go. Let's see, turn that on. Okay, let's see if that will work. And now I go maximum, and now we should, yes, beautiful. Okay, so you can see as a species level, not an individual, because some people are left-handed, some people mix, some are right. But at a species level, humans are predominantly right-handed. And we don't see this in the other species. We do see handedness in creatures like a rat. They'll put some peanut butter in a toilet tube and see which paw reaches in consistently to get the peanut butter. So you will have even handedness in the individuals in these smaller brain creatures. Now I'm pointing down here at the chimp data because this is the one I showed for 20 years. And only as good as our data. And like a lot of science is about investigating presumptions, doing multiple studies so you get the right answer. And find out, just recently I just saw there was a paper talking about doing much better research on handedness of chimps, and they found out they do have, they are more right-handed. And this is showing the vulnerable chimps and the chimpanzees have a more likely to be right-handed. The gorilla, even though it looks like it's right-handed here, the argument, the conclusion was they weren't. This is old data saying, well, the chimps are just, no, they're not, they're showing left and right equivalently, and here we are over here. But that's old data. Here's the new data, and showing the handedness becoming right-handed may have emerged, at least 6 million years ago. And, handedness is a complex process. And they find out when you look at the chimps, that depends on what they're doing, they'll use the right hand. And we have this where they usually, there's a hand that deals with dexterity. That's usually a dominant hand. And there's one that deals with like placement, keeps staying steady. And sometimes the left hand is more the the right hemisphere is more receptive. The left hand is more receptive. The right hand is more expressive in the typical pattern. And so for receptiveness, you want to be able to detect what's going on in the environment. That's probably why using the left hand, because then they can sense when the thing's moving on the termites are biting the stick when they're using termite fishing here. And that's just because the sensitivity of the receptive side over the lack of sensitivity of the expressive side. You act on the world with your dominant hand, and you receive more in the non-dominant hand. There's also in this paper, where's the name of that? It's down here. Here it is. Hopkins 2006, very exhaustive paper. Those are always good. Look for review papers. Go, a lot of times you want to investigate a topic by finding its earliest papers, because then it's not been messed up by all the studying of the method. A lot of times they'll come over a method, the study of phenomenon, and then they'll start studying the method more than the phenomenon. So the early papers, the phenomenon is being studied more than the method. And but then you want to read the early ones to find out, okay, what's the phenomenon being studied, and then find latter ones to make sure that data is consistent, and they find what they concluded early is what they still are concluding, or was it something going on in the methods that could have biased the results. So one of the things in that paper is talking about also cuddling, or cradling, I should say, cradling of the infant and its effect on handedness. Okay, well, the handedness is telling us something about consciousness at some level, our speaking brain versus a non-speaking brain. And the speaking brain and the non-speaking brain, the right hemisphere, can understand some language. It's not like it's doesn't understand, it just can't express. So how does it influence consciousness? Well, one of the beginnings to understand consciousness is what's called the mirror test, where, and I've talked about this before in the Masterclass, and you can see here the chimpanzees are using the mirror and self-referencing. But if you go to like a gorilla, they use the mirror. They think the mirror, they think that's another gorilla there. So, and there may be something about that that equilibrium between the two hemispheres. They don't have a dominant, speaking hemisphere, may be causing some of the issues. Years ago, I discerned, I think, that the chimpanzees were actually more left-brained than humans, and you can see that because of their social hierarchies. And we have more what we call flatter hierarchy in terms of mating and relating to other males, relating to other males, and that we are more right-brained than the chimps. But the reason why we are much more successful in manipulating the environment is just that we have much more tissue in our brains. Here is a longer version of this. Let's see if I get interesting. It's just doing all these displays against, it doesn't have enough interaction with the environment to understand this item, this object, and it's treating it like it's another gorilla. And here we go. We'll do the chimp one here. And the chimp one, they've got more of a imbalance where they have an expressive brain and a receptive brain. And like I said, probably even more left brain than us in some ways. You can see that it's started off saying, okay, are you another chimp? And then realizing, wait, there's some self-referencing going on, self-reflection. And that's where it stops. The reflection ends on the edge of the mirror. The baby is figuring out, what is that? Is that baby? Can I play with that child? And eventually they calmly are interacting. With the mirror. He's doing a little display. He's still figuring it out. Okay, let's go to the next one. So, well, one of the things about human evolution is that we are very neoteny. We maintain juvenile features into adulthood, and we're the more gracile of the forms of primate from our ancestry, meaning whenever there was a robustus form and a gracile form. The robustus form was the brawny type. Gracile was more the slimmer, in solving problems through intellect. The robustus eventually, I like calling them the bamboo chewers, like the gorillas, and but the gracile line is what we are. We are the gracile form of a gracile form of a gracile form of a gracile form of hominid evolution. So, okay, well, neoteny, you can see partly in this data of handedness that the gorillas here are not really, they're showing a little bit of a bias, but the juveniles show a very strong right hand bias, just like human children. You can see that this looks more like a human than the adult form, the child form. So a lot of times people think of it like we're a juvenile, the gorilla that got to maturity and could give birth. We didn't continue that adult maturation. We slowed it down so much so that we could maintain childlike features into adulthood. Okay, now one of the ways to look at how aging affects us is looking at, in some level, how old is your brain? And there's a number of ways to look at how old is your brain. A very simple measure I created years ago in EEG was just looking at how connected is it. because we all start off with the cells are all dispersed. They're I like to think of the brain as a bunch of jellyfish, the little cells, jellyfish in a way, how they have these little tendrils, but they're too short to connect them almost anything. And as they mature, they start sending out these tendrils, these processes, and they start to create a matrix throughout the brain. But at first, they're just floating in their own, milieu, and they are underconnected. And you can see this in the EEG, the lack of a connections. And as we mature, we get typically more and more connectivity, and you can look at it in terms of comodulation or coherence. And one of the measures I did was this global coherence years ago. And before I even understood the Thalfa range as being so important, I was already studying it. That's something that happens in science. You accidentally study something before you really understand why you're studying it, and then it turns out to be useful. And this is an early data set of ADD kids, Asperger kids, healthy kids, and then the healthy adults. And I think I go over this slide multiple times because the most interesting part of this slide is these people down here. I'll mention in a second, but this is just looking at how much global comodulation or coherence for this range, and those are the years. And you see just pretty much a linear function with scatter. You can see the Asperger's showing sometimes much higher than their age would expect. Here's one's much lower. That must be an unusual case. ADD kids, they're right on the plot here. Comod deals with, I like to think, the higher level, the would call the cortical thalamic networks, and the coherence is the thalamocortical, just the direction coming out of the thalamus, being controlled more by the thalamic dynamics, the reticular thalamic nucleus, and so forth. So coherence, in a way, is kind of deeper in the brain than the comod, so deep that you got to know what you're doing, because you can mess people up with coherence training, more so than you could ever do with comod. Well, the point is, you can see this great little function here, and the coolest thing is everyone down here is all got PhDs and one lawyer, one terminal degree. And the ones up here do not. I don't have them really depicted well here, but I knew everyone here. This data is a lot of it's from my dissertation. I think this isn't my dissertation, and these are all educated, and it shows you if you are putting a lot of mental effort, into your intellectual abilities, capacity, you slow down this connectivity function. In essence, like these two people here, their brain's like a 14-year-old. Same thing over here. They're acting, they're younger brains on this side. These are older brains. Lack of education makes you mature quickly in a way that's probably not helpful, because we are a neoteny species. You're not being neotenous. Education, you do maintain that slower connectivity, lower connectivity, as the younger among us have. Okay, so when did we become right-handed? Well, there's some evidence that we were right-handed 2 million years ago, which now makes sense. In fact, before, when I looked at this handedness issue, and I had, oh my God, I had this data set that said what chimps didn't show. So it must have happened sometime between the chimp separation from humans is when we became right-handed. Well, now we know, no, it preceded. It was happening in the chimps. Maybe not so strong, but it was always starting. And but in human history, as best we can tell, we've been right-handed. We can see evidence in going almost back 2 million years. And if you start looking at artwork, when they show single-handed depictions, like carrying swords or something like that, you see this predominance of right-handedness throughout the decades, throughout the millennia, I meant to say. Here, the hand outlines in the red ochre, mostly the left hand, because the right hand is doing it. So, and there's even some evidence going back about 3,000 years of the rate of left-handedness. Now, we do see an elevated prevalence of left-handedness in very talented individuals and those who are having trouble with the society, having trouble with their lives. And you can see there's a overrepresentation. Doesn't mean there's more than 50%. This means that if left-handed is 10% or 14%, which is often the number given, these show higher than 14%. And so criminals and lawyers, pretty much the same there. Autistics, math prodigies, tennis and baseball. I remember Pete Rose used to have a taunt that if when he was dealing with left-handed pitchers and got on third base, he would be saying you'd still be in the minor leagues if you were right-handed, because your left hand gave you an advantage. It gave you a different angle of the spin and the result. Same thing with tennis. When you hit the ball and the ball has different spin. And we've had many presidents recently who are all left-handed. Well, the Bush wasn't, but I think Bush Senior was. But there's something about left-handers having to adjust to the world, and that having to adjust early in life may make you a better person in politics. Okay, so we typically just ask the person what hand they have, but if they start saying, well, I can use both hands, I'm mixed, dominant, or ambidextrous, just have them write something out, and one hand, and write it out again with the other hand. And you can see usually from the scrawl on one side and the more elegance on the others, on the other hand's writing it, which hand is dominant. But there are these tests. This is called Oldfield, made this in the 70s, a test and to get at how right-handed you are or how left-handed. Most left-handers are kind of mixed in that they will use the right hand for some things, whereas you'll have some right-handers never use the left hand for anything that requires any kind of execution, any kind of real true expression. And here's furthermore, and then you can look at it, how does handedness come to be? And is it a genetic issue, and you see it in your families, and it is genetic for some, and for others it's environmental cause. What we do know, left-handedness drops through the lifespan, and you have a much lower percent as the older you go. And there's two sort of schools of thought of why that's the case. One is the modification hypothesis, cultural pressure, which I know to this day happens in some countries. I had a student from Uganda whose brother was left-handed, but in school they wouldn't let him use his left hand. You had to use your right. It was sinister to use your left. And so there's this modification hypothesis. There's also that devices are made for right-handers, and the dominance extends to your foot. So we drive with our dominant foot. If you're right-handed, your right foot controls the accelerator and brake. So that need, the constant modification driving us towards right-handedness, maybe some of the reasons why we have this reduction in this rate over the lifespan, but also that it's more dangerous, like for instance, to drive with your non-dominant. And that's why this rate drops, is because those who are more left-handed are in more danger. And we know that coming up right here. For instance, 6 times more likely to die in an accident, 4 times more likely to die while driving. It's also the elements before of why you became left-handed. Sometimes left-handed may be genetic or random in essence. Other times maybe from early brain injury or even later brain injury. But we do see sometimes the advantages in left-handedness in certain aspects. Well, this one's not going. This one's showing how hard it is if you're left-handed to use some of these devices. This is a right-hander using this, but a left-hander, you got to put your hand in the danger zone for the circular saw. So that's why you get these. You can cause accidents readily. Okay, so what's the cause of left-handed? There's 3 general ideas. One is that there was early damage in the womb or right at birth. And they've seen this over 100 years ago, how there was more left-handed in the special education facilities than there were in normal schools. And so the idea that there was some damage, excessive testosterone or something was going on during the gestation, probably when the brain was forming, and at the 3 months, first trimester, beginning of second trimester. And that damage caused the motor strip that would have been the dominant motor strip to be compromised, and thus the other side took over, and that's control the left hand. So there's that element, that's part of it. There's also, we know there's some genetic to it. If you have, the argument is that there's genes that push us to be right-handed, and like if your parents were both left-handed, the chance of you being right or left-handed is kind of 50-50. And there's also this other one of mirror twins, and that's what I'm showing the Shinings twins here, where 1 in 8 pregnancies, conceptions, 1 in 8 conceptions, actually the zygote will split and it'll be twins inside, but only 1 in 80 births are twin births, meaning that 90% of the time, one of those parts of the zygote that split into another fetus got absorbed very early on, probably by the placenta. Sometimes gets absorbed by the other twin. You know, and the person is born with some cells on their shoulder or something, which was their twin. But in that mirror twin, we know in the twinning process zygotes, you get the left-right switch, and you get, like, you know, freckles or moles or something on the right side of the face of one twin, and that on the left side on the other twin. Well, same thing with handedness. That there's this duplication, this mirroring effect, where one was right-handed, one was left-handed, and then you get the right-hander got absorbed, and you're born left-handed, and you're the left-hander, and you're all alone coming out. You're one of those 90% who were not absorbed. You were, I mean, the 10% that were not absorbed, you were come out of and you had a mirror twin that was absorbed, and that's why you're left-handed. So it could be brain injury, genetics, and genetics just look for your parents, and there in terms of the right and left-handedness, and the mirror twin hypothesis. Okay, now the problem is you got to choose a hand, just like the gorilla. Gorilla doesn't choose the hand, and that way doesn't have a full development of consciousness, because that handedness is indication of your brain organization. And you think of your brain as like you have two vehicles, and two vehicles, and one vehicle, you don't want to duplicate the functions in each vehicle. It's best to do, okay, instead of having 1,000 functions on one side and having a duplicate of 1,000 on the other side, have different functions. Now you got 2,000 functions. Well, when you're not doing handedness, you're not getting the duplication of functions. And so there's a deficit. You're at half, something like a half of the functions you could have if your two hemispheres are being not differentiating enough in their abilities. And we see that mixed handedness is higher in autistics and in schizophrenics. Now, you're not schizophrenic at age 7. This is British data where they collect data like every 7 years on these kids, and they go by age 25 or so, or 28, you show schizophrenia, and they go back to the data and found out, wow, these kids were it makes handedness. So in a way, you want to drive the brain. One of the ways to drive the brain to lateralization is to make sure you're using one ham for the expressive stuff and one for the receptive stuff. Okay. So this is the water test is showing it up, and this is an example of when they're doing asking the name something. Showing that again, and you can look at during fMRI which brain area is doing the speaking. So you can do it like that. There's a lot of individual differences. This is sort of really gross image. A lot of individual differences. This is in terms of organization. So generally the argument is that females are less lateralized than males, maybe especially in the frontal lobe, but it's still there's still going to be a spectrum. And that's the whole thing about neurotherapy, is we're doing personalized training, and we're finding out how you are organized and optimizing your brain, not a general brain like they do in some training techniques where they just try to drive you to the slow functioning general brain, the goose step training techniques, Z-score and stuff like that. So here is Ojaman was using an electrical stimulation and having the person speak, and wherever he'd hit part of the brain, the exposed brain, and the person would be speaking, and they suddenly stop speaking. And this is the areas across the 117 patients. And these are the zones that would stop speaking. We generally create meaning back here, Wernicke's area, and we express out here. This is we do the motor articulation, Broca's area. Okay. All right. So this is a freaky image. So the initial trying to figure out what's going on in terms of brain function was very symmetrical. Gall, who sometimes is criticized for phonology because the idea didn't fully work. Obviously, your skull doesn't really reflect what's going on in the brain very well. However, a lot of concepts were sound, and some people like to criticize and say neuroimaging is modern phonology, but that's like not really understanding the picture that brain functions are largely in areas, and this distribution of function, and we see that with like stroke recovery and so forth. But there was a value to the concepts of this plurality of organs, and it just comes down to you just had to get the right level of understanding what is the functions being served, and then in this case the functions just too high level, mirth and so forth. I've gone over Gall in the history of neuroscience of how he came to be, so I'm not going to go over that again today. So there was evidence early on of functional laterality. It's just that unfortunately it was in these small sets of data, and Billiard almost got there, where, like for instance, Magani in 1761 had looking at phasics, and for whatever reason, well, that says monophasic, it's hard to see there, but he had mostly aphasics in the left hemisphere, and the problem with pathological populations are often going to be reverse organized. They're going to have things that is unusual about them, so it's hard to take pathological populations and generalize to the norm, to the healthy ones. But he was 4-to-1. I know it's hard to see, that's 1 there. 4-to-1 on the left side. His 2-to-1 in this data set, and then final data said it was 3-to-0. And if you done, none of these would have been statistically significant if they had statistics of that level at the time. But if you had done a meta-analysis, hey, guess what? Left hemisphere damage is more likely to cause aphasia than right. So he's really out over here. He determined though that the front of the head, the frontal lobe, was needed to have damage for there to be aphasia, but he didn't see the left-right difference. And the first person to detect the left-right difference is Mark Dax. We don't have a photo because this is one of the sad things of science, that it has politics involved, and he was a country doctor in the south of France. His son published his father's memoirs showing that left hemisphere damage was associated with verbal issues, but it got really no attention. Only scholars really would know his name, because the data, in fact, the publication of his father coincided with Broca's stuff, and then Broca got all the credit a few years later. So, and Broca was highly connected. He was in the political realm of science there, and there he is. So much so that we call this Broca's area. He had a patient who could only say the word ton, and after he soon died, they found out this deficit over here on the left side, and that showed that, oh, we speak from the left hemisphere. Nous parlons avec le hémisphère gauche. Now, I read, but I have not been able to find again, that like the 8th or 9th patient he saw had a congenital issue over here on the left side, and so it wasn't well formed, and the person had the aphasia, trouble speaking, and they had right side damage, and because this thing never developed on the left, so the right side took on the language, and that is good damage, and that caused the aphasia. So early on he found he studied atypical. I've not been able to find that again. I read that, I was reading even French papers years ago, and I remember encountering that, and every time I mentioned, no one knew about that. But so he encountered an atypical example. We had an atypical example come into this field of a kid who got his head crushed between some boats, and he was deaf early on, and so he got damaged in the Broca's area, and the neurosurgeons were afraid to deal with it, to remove the damaged part, because he won't be able to speak. But father convinced him, well, he had these years of being deaf when he was a child, or issues with language, and maybe the other side, the right Broca's area had developed enough, and sure enough, when they removed the left side, he was able to speak again after some time. So he was atypically organized, or mixed organized in that respect. Okay, as I talked before in the history of neuroscience here, after Broca, we have Wernicke finds another form of aphasia. This is the halting form where they can still say meaning. Well, Ton couldn't say anything, but sometimes you have Broca, they can say meaningful words, but they can't. They don't have fluency. They don't use the helping word. So an example would be you could, I say, saw a cat walk or something. You would not be able to say, I saw a cat walking by this on the road. You wouldn't be able to say something that has all the flow that we would expect if you have Broca, damage to Broca's area here. So that's articulation. Back here is meaning, and this is where we generate the categories that we want to string together and put them in an order, syntactical order, so they make sense, grammatical order. And the people who have damage to Wernicke's area will just talk gibberish. They'll be fluent, but it'll be meaningless gibberish. And if you go on YouTube, you can find, just type in Wernicke's aphasia, get an example of Broca's aphasia. There's some nice videos out there. There's something, learner.org has discovering psychology, it has the mind, and has the brain, these two teaching modules. It has a lot of videos of patients that will be helpful to see if you're interested. Well, so the left hemisphere was viewed as, okay, we speak from the left hemisphere, that's the mature hemisphere, and even some people this day would say that the left brain is the most important part of our consciousness. But John Hillings Jackson recognized that no, there's some functions the right hemisphere is superior to. Visual recognition, as we started off here, emotional perception or emotional recognition in faces is the right hemisphere strength. And one of the things to understand when you're dealing with lesion work is that when you find a lesion, it doesn't mean the thing was finalized there. It means it just, you broke the chain of events, the sequence. And this is Dr. Head, and there's also a Dr. Brain studying the brain as well, giving this nice phrase, which I've talked before. To locate the damage which destroys speech and to localize speech itself are two different things, because it's a network. It's like just you find a problem in the network doesn't mean, and that's where it stops the processing and causes issues. Doesn't mean that that's where everything's done. It just means that's the broken link in the chain. Okay, well, coming down to the functional asymmetries, how the hemispheres are different. One of the most interesting things is unihemispheric sleep that you see in dolphins. They sleep one hemisphere at a time. They really don't have dreams. They may have little micro REMs, but it's very hard because when you dream, your brain goes into atonia, lack of motor movement, and they sink. In fact, if you anesthetize a dolphin, which was done in the 60s, early 70s, they would die from being anesthetized. You have to make sure you keep them breathing. That's why they have to be sort of awake all the time, these marine mammals. So this is the wake hemisphere. But they go into this, they're not like when they're in this state, they just sort of hang in a pod together, sort of just drifting together. You can walk up to them and they will engage you, but that's because they're waking up when they see you. But they're in this sort of, even though this is conscious, they need both hemispheres to be awake, to really be awake. They're going to be in this sort of stuporish state, but they are paying attention to the environment. They'll have an eye open to the outside of the pod. So the eye to the other side, towards the pod, centers closed usually. And there's some evidence we used to have unihemispheric sleep. There's the ear, the listening, our sensitivity at night when we're sleeping goes back and forth between the two hemispheres. But it's more consolidated sleep's much more powerful, having both hemispheres in that slow wave state together. So you find right hemisphere and left hemisphere dominance. Right hemisphere dominance often follows what we expect: spatial processing, facial recognition, all the way down to even these primitive mammals and birds. Production of vocalization, left hemisphere. So it's a basic mammalian quality of the expressive side versus the receptive side. We see now, going to the anatomy, left hemisphere, there's something called the cerebral torque. There's another name for it, but that's the easiest term. And this is why we have more, when you're looking at a face, usually there's more of the right frontal lobe than the left. And that's why if you take a face, cut it in half, put the left side on one side, both lefts, duplicate them, rights, and the right side duplicated, look like a wider face. and we've done this for a long time. And that's one reason why when we're doing neurofeedback, there's certain brain areas that are they don't show symmetrical center points on the left and right side, like area 11, for instance, and 19. So we adjust for that. Okay. All right, well, understanding cerebral differences or hemispheric differences, a lot of it is about the corpus callosum. Corpus callosum is this wiring between the two hemispheres. And the most interesting thing about the cerebral hemispheres, how they're wired, is how the thalamus is hardly wired. These are probably wired, the inferior and superior colliculus, but the thalamus is not. I like to call the thalamus our parents, and these are the children out here, and our ancestors are back here, cerebellum. Okay, this is a nice little animated view of the corpus callosum. Now, supposedly only 1% of the cells have callosal connections, but then they branch out on the other side, and they affect. Sometimes the number is 10%. You know, this is like when you're studying the brain at this level, it's like studying star systems. It's always hard to, because you're sampling these very small areas to see what you're looking at. This one makes it look like it's so global, but it's more like probably 10% on each side connecting. It's about 200 to 250 million fibers in humans. It emerged in placental mammals. So if you go to like kangaroos, marsupials, they don't have the corpus callosum, but they have what's called this interior commissure, which is really hard to see. There's the interior commissure because it's cross section, it's hard to see. Interior commissure has the most of any structure in the brain, has the most variability across people. It has a 7-fold variability, meaning that some people will have these big pipes connecting, and the interior commissure connects the like area 38, which deals with sense of self, and other deals with orbital frontal, governs our behavior, and they will be 7 times bigger in some people than others. And that's one reason probably why we have alexithymia. People cannot communicate their emotions because the interior commissure is just a tiny little straw. It's a paper straw. It doesn't connect. There's not much of a pipe line between the two hemispheres. You also have the hippocampal commissures. And the most interesting thing about hippocampal commissures, are often used as the 0 point in when they're doing 3-dimensional referencing of brain volume, brain areas. And then you have this little thing called the massa intermedia, which is like a fibrous thing. Doesn't even look like it's an axonal thing. It's more just to keep the thalamus somewhat together. And when Joe Bogan, who cut the corpus callosum of split brain patients, the first set of them, or actually the second set, the first set was unsuccessful in the 40s, but the first successful set with doing callosotomies, he said, I cut this thing even though I didn't know what it did. I didn't believe it. You know, I made sure there was not a connection there. The reason why he did that, actually I should wait till I have the slide coming up with him. It's coming up. All right, so let's get with the corpus callosum. This is a beautiful view of showing it. I don't really, is it that much connection? Well, let's think it is. A lot of these are artistic depictions, because I thought it was more like 10%. It looks like more like 40% or 60%. Connection. The organization, here's the front, the genu, think of like kneeling, genuflect, looks like a kneeling in there. You have a little thin part, the isthmus, like the isthmus of Panama. You have the isthmus of the corpus callosum, and the splenium is in the back. And the fibers go straight across to each other. They don't go diagonal. They find a few diagonals, but they're all language based, and they're very few. It's most of the wiring goes right across to the homolog, the other side. And as I've talked before in the previous masterclass, is how the more myelin you have, the faster you go, and the shorter the refractory period is, and so the more you can process. And that big wiring happens back in the splenium. It continues. There's a gradient of myelination going on, but the front of the head doesn't get fully myelinated to age 50, temporal lobe to age 50, 45, 50. Doesn't get its max, but the back of the head gets done by like 10 or 11, which I like to say sometimes is why 10 and 11-year-olds can be sometimes obnoxious, because they're equal to their adults in their functions served back here, but not the social functions. Okay, so the connections we do see in the corpus callosum and the ipsilateral pathways, most of the connections go to what's called homotopic or homoaerial, meaning it will connect to its governing site, the yin and the yang, and whenever it's strongly connected to on one side, it will also do some nice connections to those other partners over here. You think of it like spouses, and this is your family, and well, these are the kids of your spouse, and you also connect to them. Not as strongly as ipsilateral, but you get this real strong connection is the spousal one, the homolog one. The heterotopic one is the one that only shows up in a few language areas, and it's very rare, meaning very sparse, might be a better way to say it. Ipsilateral, there's a lot of ipsilateral connections within a hemisphere, like this, for instance. Okay, so when you do EEG, there's really nothing connecting, no monosynaptic pathway between, like when you go this diagonal like that. The things, if you're coordinating these pathways, it means that there's a homolog one and an ipsilateral pathway. So this is the hypotenuse in essence. Well, it's really the sides where the wiring occurs. And this is just a depiction of how you can see that the homologs connect to homologs. They with just a few language pathways, and it's, like I said, sparse. Okay, so what is the function of having this other hemisphere? What value is it to have 1,000 functions on one side and 1,000 complementary functions on the other side? Well, sometimes you can. The idea is, okay, it's transferring information from one hemisphere to another. We can see that in various tests, and some I'm going to show coming up. You can stop the hemisphere, and you can inhibit that processing, and we see that sometimes in stroke, for instance, with someone, we know right hemisphere language exists, but the stroke area, the broken area will still be trying to govern the other hemisphere, the homolog on the other side, and that causes disturbance and causes the lack of ability. Like if you can knock out that it's like having a bad governor, causing issues. And this thing called homotopic inhibition generating the complementary percepts. So like if your left hemisphere is thinking about arms and legs, the right hemisphere will inhibit that and think about all of the associates around it. That's kind of an idea. But obviously these are kind of crude ideas. And depending on how you study the brain, we'll see more involvement. We learned, for instance, early on, it was a Ron Zeidel study where you train the right hemisphere, it was C4, and you get improvements in the left. And you train the left hemisphere, you get improvements in the right. It was the governing, fix the governor, and the hemisphere thing that was governing the opposite side does better. Fix the spouse, and the other spouse does well. Okay, and here's a Ron Zeidel right here. Here's Bogan, and here is Sperry, who won a Nobel for this work. Sperry and Bogan worked together, and Bogan he got the Nobel Prize, Sperry, for doing hemispheric differences, and Bogan should have deserved it, but they can only split it. They do a split of 3, and Hubo and Wiesel were the same years as Sperry's. So Joe lost out on that. He was viewed more as a technician. He taught me a class on consciousness, so that's why I'm laughing. And then Ron Zeidel was my advisor, one of my 2 advisors at UCLA. And he was a student of Sperry, and Sperry had a famous student, Gozaniga, who was studying left hemisphere functions, and Ron did the opposite, studied the right hemisphere. Okay, well, one of the things that Sperry found out really early on, some people will say, in fact, but Joe used to say that Sperry won the Nobel not for his hemispheric stuff, but for the neuroplasticity work he did before the 50s. And so they awarded him the right prize, but for the wrong work. Not unusual. Okay, so here's a study where they looked at, where they blocked the perception of one eye, and they allowed, they had everything intact, so that you just training one eye. You can think of the hemisphere connected to that eye on a task of discrimination, like there might be cat food behind the door that has, or push the lever if it has this, push the lever which has the circle and not the square, or the square and not the circle for the food to be revealed or to be distributed. And once you start off and it's 50-50, they don't know which one is the cue, and eventually start finding out the circle tells them that's going to be where the food's behind. And so it takes some time to learn. And then when they finish, get 100% accuracy, is always like that's pressing the lever that has the circle on it to distribute the food. Let's make it that. They move the patch to the other eye, and it immediately has 100% success. Immediately starts still pointing to the left, to the circle, and that's because this whole brain is intact. Wow. disconnect the brain, disconnect the optic nerve, so that now you're only training one hemisphere at a time. If you do that, you get that learning curve. But when you move the patch, once they get 100%, this hemisphere never learned. It didn't have the coordination, didn't have the hardware wiring to figure out what was going on. So it's back at ground zero and it starts again. So this is showing how isolate from sensory information and disconnect from the other hemisphere shows evidence of functional independence of each hemisphere. You got to have the wiring, and at a high level. They probably didn't cut all the way down to the colliculi. I think that could even kill the cat. They cut the corpus callosum and the optic nerve, and that's show that isolated, it didn't learn, it wasn't receiving information. Okay. Species differences exist in the anatomy and functions of interconnecting hemispheric commissures. Some primitive marsupials do not have I mentioned that already. Some birds, although having interhemispheric commissures, behave as humans who do not. All right. And here's the research. What it was, they looked, and it's all about controlling seizures. And they in the 40s, they did some studies in Rochester where they cut part of the corpus callosum, but they did one opening into the skull, tried to cut the whole thing, left some of the corpus callosum intact because they couldn't reach it with the opening. They only had one cut, and the seizures would propagate, and they caused seizures. So what was going on with the callosotomy, which Joe Bogan was trying to reintroduce? They're just trying to stop the person from falling. So they have a grand mal instead of, because once the grand mal, it hits one motor strip, let's say left motor strip, and it propagates to the right motor strip, now you have no control over your motor system and you fall on the ground. But if you could stop that transfer by cutting the corpus callosum, even though if one side of your body is shaking, you can still control your other side, so you won't fall and hurt yourself and possibly break a bone or so. Well, when they started doing the callosotomies, they found out not only did it stop propagation, they actually stopped the seizures. So there was something about seizures that needed the other hemisphere to be involved. They had to ping back and forth across the corpus callosum before a seizure would erupt fully. And by cutting the callosum, they were able to stop the seizures. Well, he said he had to do 2 openings in the skull. You got to get to all the areas, and he cut all the way down there to have successful callosotomies. One thing about callosotomy, you look them up, they call it split brain research or experiments, is a lot of times people will ask them insights, because you're talking to the left hemisphere now. You're talking to the expressive brain only. And the problem is they don't have the insights. Like it's like a philosophical questions you would ask of them, like, how does it feel now that you don't have this other part of your consciousness? And they don't know. They can't really tell you. Nothing seems changed because the left hemisphere only knows the left and the right only knows the right. Okay. So that just shows the corpus callosum. And you're actually going to have to damage. Usually you have to push one of the brain sections to get access to this wiring, and so you always squish the right hemisphere. That's what was the standard thing when you go in here and squish to get access to be able to visualize the corpus callosum. So there'd be a little compression damage on the right side as well. All right, showing the callosotomy, cutting the corpus callosum. And what you have, the callosal syndromes, immediately after the surgery, you get these weird stuff where the non-dominant hand doesn't have any kind of expressiveness to it. You have competitive movements, which I'll show you in a moment. Alien hand, where the person's confused. What is this hand doing? And I'm picking out my clothes, and it's picking out different clothes. And they also masturbate all the time because it's like you had this hand that wasn't yours, and some weird stuff was going on there. Joe said he would walk in on them right after the surgery, once they started getting healthier. But as time progressed, the most interesting aspect of the split brains is how they look ordinary. They didn't look anything outside. You couldn't detect that they were split brain within a few weeks. The only way you could detect it is by doing tests, by doing very specific tests to show that disconnection in the hemispheres. They would also compensate a lot. Like we have this one guy named Lenny who learned how to let his one hemisphere communicate to the other with like his eye movements. So if the answer was a yes, he would look to the left, and his right hemisphere notice he's looking to that direction. That's the yes and the no, and he found the way of cheating on the tests. They often maintain being very polite for decades, that they knew these people working with them. So they Aram once mentioned how he was working with these people for many decades, and they still were very polite to him. They had like they didn't know him, and that's because the right hemisphere was not part of the speaker. It was disconnected, and just like you see sometimes in people when they have that interior commissure smaller than it should be, you get like alexithymia or inability for the emotional to connect with the expressive side, the intellectual side. Self-focused, you talk to them, they think the left hemisphere thinks everything's inside of it. Right hemisphere, everything's outside of it. So they just think you know everything. Like I remember the first time I met one, she started talking about, remember, she said something like, well, Charlie's down by the lake at that cabin where we had that issue. And I just met her, and she had no understanding that I did not know. And she was not sensitive to the informational needs of her audience. That's one of the things they talk about in terms of schizophrenia. Well, in split brains, the same thing, because the two left brain, the two, I think everything's inside of them. And there is this lack of transfer, but it's very hard to detect. You gotta use various tests where you show the images only to one visual field and then ask them. And it's a very special test you have to do to really see what's going on with the syndromes. Okay, here's an interesting thing. Watch this. So this guy's going to do the split brain. He's going to do the block design test, and he's going to have competition. Now, the right hemisphere can handle spatial relationships. So the left hand is controlled by the right hemisphere.
Solving the problem. When the patient tries to solve the problem with his right hand, which is governed from the left hemisphere, we find that he is not capable of doing it. Namely, that the right hand, which is governed from the left hemisphere, is intrinsically incapable of performing this kind of visual constructional tasks. It's interesting to note that the whole perspective is gone. He has 3-in-1 block combinations. It doesn't even square them up. You can see the left hand wants to keep helping the right and is interfering. Well, we've now seen that the left hand can perform the problem and that the right hand cannot. Now the question becomes, what happens when you allow both hands together to try to solve the problem? And what we find out is that they fight over each other. One hand knows how to do it, and one hand does not, and so they more or less squabble. And the reason for this is that the hemispheres are disconnected. Now, the right hemisphere controls the left hand, and the left hemisphere controls the right hand. And these are almost mutually independent systems. It was as if two people were fighting over performing this task. One knew how and one didn't.
Okay, so that's almost a farcical view of how the two hemispheres are like two different people when they're split like that. Well, you can query the right hemisphere. It can't speak back to you, but it can draw and it can write. So you can show something and ask them, what is this? What did you just see? And it's going, if it's in the left visual field, it goes to the right hemisphere. I don't know. Well, can you draw it with your left hand? If you ask for the draw with the right hand, they won't draw anything. That or anything that's relevant typically. Sometimes you get a little bit of the content with the right hand. It's very interesting. And there's like I said, I think Discovery Psychology had a good video on that, showing us the split brains, where there was a little bit of communication through the colliculi if it was important information. But most of the time, they can't do anything with the right hand is what they saw in the right visual field. There was nothing there, and they draw. But if you ask the left hand, they will draw something that's relevant that shows that they understood what they were looked at. Now, when you do this flashing tasks, it's got to be just for like 200 milliseconds. You do it like 180 milliseconds typically, because when the moment it flashes, your eyes are going to move towards it, and you want to make it only in that one hemisphere. So it's very specific apparatus or procedures needed to test the split brain. And you can go looking at which items go with what, and depending which hand you're asking, which hemisphere you're asking, you see different things. Okay, now you can do tests in split brains, but also in typical humans, intact individuals of the hemispheres in terms of language and sounds. And they do what's called dichotic listening tasks. Monaural tasks is when you have one sound going into one ear. Dichotic is when you have competing sounds going into different ears, and you see, okay, you ask them, which one did you hear? What did you hear is what you say. No, which one? What did you hear? Did you hear ma and pa? Well, when everyone went into the left ear that goes to the right hemisphere, I mean, right ear going into the left hemisphere, that's what they heard. The left hemisphere is the one that will respond back to you. And when you do the various tests, you find out the left ear, which is the right hemisphere, is good for melodies, configural information. The left hemisphere, right ear, is good with spoken letters and words and other things. One of the things is the I was going to say the config. This is configural information versus categorical information, and you can see that when they do this. This is the left hemisphere has all this advantage of very categorical information, even backward speech. The left ear deals with configural information. Oh, what I was about to say is that there is an ipsilateral pathway, it's just not as strong. So it isn't purely contralateral. One ear goes to one hemisphere. There is a ipsilateral pathway, but it's like weaker, 10%, 20% of the fibers. And so there is an ipsilateral. So there can be, and this has been shown in some experiments, but it's there anatomically. Well, so the right hemisphere deals with configural information, left categorical. And in terms of competence, left hemisphere has all the competence of basic language skills. What it misses is the contextual information. So it will collapse the categories, collapse the core, but it loses out on pragmatics, like knowing what it means. If you ask someone, do you know what time it is? That's a request for them to tell you the time, not for them to just answer, yes, I know the time, and walk away. Paralinguistics is the sounds you make around language, like and so forth, to help flow. Humor, they have trouble with humor, metaphor, and theme. They don't have that contextual information, that narrative processing. That's a configurable ability. And so the left hemisphere is great in the parsing the parts, but not in the wholes. So it's the local versus the global, and you'll see that dichotomy again. And the right hemisphere, it's got, can't do speech, but it can communicate through writing. But it has less of a verbal memory. Like you hear sometimes short-term memory, we have about 7 ± 2 items. That's the left hemisphere's verbal memory. The right's more like 3 ± 1. So it has trouble in all these other, the parsing. Non-imageable words, abstract words, only the left hemisphere can handle. The concrete words, the right hemisphere can handle. Here I have like these ones, high imageability versus not. These are low in imageability, I'm supposed to say. Tenacity, sincere, courage, lack. Okay, let's throw them up there. All right, so we know the two hemispheres have different styles. And again, not everyone's going to be strongly lateralized. Some people are going to have more mixed lateralization. So it's not a uniform distribution of every person's going to be left brain or every person's going to be right brain. But we do see in general, the left brain skills stay the course through our lifespan. We lose our nonverbal, we lose our right hemisphere ability unless we need them. Unless you're like doing graphic arts all the time, doing all kinds of configural information, maybe acting, doing emotional expression, stuff like that, you might keep that one up. But the verbal is required for success in our societies, our culture, so it maintains. I've shown you this is one before, just showing that in a previous, I do a much better description of this, but just showing that the left hemisphere doesn't, only the little verbal corrections you make in doing this left and right brain tasks, only the verbal corrections are great, accurate when it's left hemisphere tasks. Right hemisphere is doing the task, the verbal corrections are chance. But I've shown that before. One of the things we're detecting if the right hemisphere is dominant is by doing what's called these street tests, these perceptual closure. That's a rabbit, that's a sailboat. Almost everyone can see that one. This is a hard one. It's a knight on a horse. And what his left brain can't figure out, I could not figure if he looks for the parts. Well, what is that? How can you say that's definitively a hoof? You can only say it's a hoof in context, in configuration. So this is evidence of how right brain individuals will see this one, and left brains typically won't. Same thing with the rabbit. This is a test. It was made in 1944, so it has things like pictures like that. President Garfield. You wouldn't know it's President Garfield nowadays, even if you were very right brain. Further tests where there's more visual noise. This is actually a faucet like you might have on the outside a house. There's the handle, there's a spout, like a bell, a well right there. Okay, then there's a left brain test people often would do, and it's a categorical test. What category do these two items fall into? Tomato and cucumber. No, vegetables. Coat and dress, apparel, lime and strawberry, good margaritas. The fruit would be probably a better answer. Wagon, bicycle. And you keep going down here. Fly and tree is the hardest one. But most people can figure out it's life of life. But okay, so they've done this study where they look at how good you do on the perceptual test, the perceptual closure versus the categorical test, and get like an index, a ratio of how left brain versus how right brain you are. And showing, this is actually showing more right brained in architects and scientists and more left brain in mathematicians. It's an old study, wouldn't hold it. That's why I'm jumping over it. The most interesting element though is we all start off right brained. We become left brain through language in the first few years of life. And we can see this continuing of this left brainedness in industrial cultures, but you get right brainedness in the more non-industrial cultures. And they were studying Hopi Indians, and they went out in the outback, and even urban versus rural, we see differences where they're more right brain in the rural, maintaining configurations. So population density makes us left brained. And well, here it is. High population density, right hemisphere child becomes left brain hemisphere dominant adult. Where in low population density, we maintain right hemisphere dominant. We maintain the more initial state that we were. But schools, the larger the school, the more left brain we become. And I've gone over this study before, which is I had these students, and I asked them when they graduated from what high school, and I got their high school size, and I had them look at these 10, and this is the average 70% of them versus down to 50% of those who went to the large high schools, because the large schools made them left brained, and the smaller ones, high schools, let them, the right hemisphere develop more fully.
Well, one of the criticisms you hear about functional dichotomization, about nominalization, is that it's like too simplistic. Well, this is Bogan responding to this 30 years ago with his wife. Conceptual tightness is desirable in science. That helps us, propels our ideas. Capturing the essence rather than all the relevant facts need be no more predictive to be valuable than, say, the notion of natural selection. Saying, you have this envelope of understanding. It may not capture everything, but it does give a lot. This is why calling someone more left brain or more right brain can be helpful. Dichotomization meets the specific needs which arose outside of neuropsychology, such as the verbal versus nonverbal intelligence. We understand cerebral specialization better when we see all the activities of our hemispheres as reflections of the same underlying design. And that's partly just, you can even see in the anatomy, the left side seems more focal, and the right side is more distributed and distal in its networks. Okay. Well, this has been, people recognize this duality of the brain since 1844, when he had this man, Wigan, had a friend, where was it? If one hemisphere, so he had an acquaintance who died suddenly. At post-mortem, one cerebral hemisphere was missing. So he realized, wait, if one hemisphere can do everything, why do we need two? Okay, so to divide the hemispheres, what they could do, this is a summary. The left hemisphere is more verbal, more sequential, more temporal, digital. Maybe I should go back and forth because it's easier. Verbal versus nonverbal. Well, nonverbal is not really a good description of something. It's just the opposite of verbal. But sequential versus simultaneous or parallel, things being done in parallel. Temporal versus spatial. Think of language, temporal, but visual, spatial. Digital, categorical. I think categorical and configurable is the easiest. So digital versus analogical. Analogical means that the representation, the symbol, reflects something about the phenomenon that you're showing. Routinized, familiar, it's probably a better term, novel. Logical, analytical versus holistic gestalt. Propositional, and what Bogan created this term, I believe, apositional. Just say it's the opposite of propositional with this meaning. This is more just receptive, configurational. And here's a nice summary in the various elements. We show the right hemisphere has a lot of abilities. In fact, you see more on this side, but the left, these seem to be more valuable in some ways, and that's why they retain for our social status. The left side is more important in some ways, but the right is why we get along with each other so well. So, let's see. Okay, so there's this issue sometimes in psychopathology about one hemisphere being overactive. Often, we don't want the right hemisphere to be overactive. You see this in PTSD and maybe even schizophrenia. At least there's some lack of activity going on there. So there's an asymmetry there. Usually it's like too much left brain up here, and that creates paranoia and not enough social functioning. And, you know, it's one of those ones where, here's an example saying there's not enough left brain. So it's one of those cases where the cerebral asymmetries in psychopathology can sometimes be confusing. This from 20 years ago talks about psychoses as a breakdown of the language systems of dominance failure. I mean, you lose that left hemisphere control of your behavior, and if you have too much right hemisphere, if you're in a really safe situation, great, but just a normal situation, suddenly you're worried about danger, because what's going to come at you cannot be danger if it's routine, or you wouldn't be alive. So decreased language lateralization leads to more severe hallucinations. Disruption of idealexality, distinguish slots from the speech output or others. Failure to inhibit the right hemisphere's contributions. This was their model. Let's go in here let's move this on. There we go. So this is I had to deal with a couple schizophrenics, and this is one where we're doing, it's funny, whatever measure you're doing at the time it seems to give you something, even if later on you don't care. Like, we don't really look at co-modulation anymore. This is probably alpha co-modulation, and we saw a deficit here in that right frontal lobe area, which deals with social functioning. Okay. And the argument is, with this, that the left hemisphere deals with familiar, the right deals with novelty, but danger can be novel, and danger can be usually not routine. We want our left brain in charge at some level. I like to say left hemisphere, everything's inside of it, believes everything inside of it. That's why it can parse it, break it into parts, doesn't care about the integrity of the phenomenon. Right hemisphere, everything's outside of it. That's why think of artists being more right brain, maintaining those details, the configurations of the stimuli and the phenomenon. And that's the easy way. And so if everything's always outside of you, that's uncomfortable. That's why you want to get that left hemisphere dominance. And when you get too much stress, you lose that left hemisphere dominance. You're constantly letting the environment intrude. In fact, in neurotherapy and default network training, the real goal is to stop the environment from intruding on our goals. That's really pretty much it. You need to collaborate with others, but that is a process, not typically that spontaneous. We don't want those spontaneous interruptions by the environment. And the limbic system is prepared. It's the reptile part of ourselves, our frog brain that responds to all the environment. That's the thing we want governed. We don't want it over responding. We want to stay in our goal state, stay in the slipstream of our consciousness. Well, we have right hemisphere dysfunction. What we see in people who have lesions, lack of self-understanding of state of self. They don't realize sometimes when they're injured or they're in the hospital why they're there. Lose face identity recognition, post-spagnosia. Emotional tone recognition is lost. Sometimes there's delusions of other people being the same people. Ego boundary is disturbed. Social awareness, theory of mind. Deception detection, they see that where even if you have in deception studies, like in dementia and frontal temporal dementia in particular, they'll do a study where they have someone constantly indicating the wrong direction or the wrong answer, and the like an orderly will be there while the doctor's giving an exam, and the patient keeps looking through the orderly, even though the orderly's always telling the wrong answer, still doesn't pick up on that this is deception. Always thinks somehow that's the person's helping him. And like we saw earlier on with the handedness being messed up, and that's a hemispheric, not enough lateralization, and you do see it in autistic spectral disorder. This is a study. There's all kinds of studies. I don't, it's one of those things where what we do is personalize. So we don't really care about the general pattern. It doesn't make a difference what the general pattern is. We're going to do a brain map, see what's going on specifically in your head, and do the training based on that. With some concepts about we want to get balance between the two hemispheres. And when we say asymmetries, we definitely tackle those with higher priorities. Here's one talking about a lack of right hemisphere material in Alzheimer, but I'm not sure how well that holds up. And here's another one on gray matter. And again, generalized things, it means that these behavioral envelopes, these diagnoses are sometimes useless. They don't help us solve the problem. And I think most people, if they were honest, who are even outside neurofeedback, would say a lot of these diagnoses don't help us all, because like you say, someone comes in with depression. Well, depression typically means a lack of gray matter in the area 9 in the front, but not always. And then you have to figure out so they give a med for this, a med for that, and it just takes a long time because that med doesn't work, and then they go to the next one and the next one. You got a personalized thing. The generalized description, it's not very helpful. It's like saying, well, this person is an animal. Maybe that's a bad metaphor, but I'm trying to say, you got to say what kind of animal. Is it a llama? Is it a squirrel? Just it's too wide a category, and that's a faulty element of science when your categories are too wide, too inclusive, or too exclusive. They lose communication value, and that the whole function of generalized. These looking for uniform problems in these diagnostic categories is just messed up because it's too big categories, too inclusive most of the time. Okay, when you talk about hemispheres, people want to know how the hemispheres are in terms of emotions. There's many ways to describe emotions. It's hard at some level because it's with language, where the left hemisphere is trying to describe this non-linguistic element. One of the most prominent and popular is to say we have 6 basic emotions, but there are other people who talk about we have 842 emotions, or we have 12 or 2. And this sort of the sad thing about this is that of the 6 in this primary assessment of emotion, really only one of them is positive. Then you have surprise could be positive, and the other one's 4 negative. These are my children showing them all. Okay, when they're younger. That's an old photo. Okay, so let's get some confusion going on here. Is the left hemisphere the positive hemisphere and the right hemisphere is the negative hemisphere? Well, there's some evidence to show that that's true. The left hemisphere expresses positive emotion because when you have damage there, you're more likely to get depressed if you damage the left side, meaning you're unable to create the positive emotions, and less likely if you damage the right side. Well, that's good evidence. Yeah, it looks like the left is positive. Let me jump. I'm going to come back to that because here's the opposite one. Wait a second. Let's look at this one. So is dealing with mania, what should be very positive. You see that after right hemisphere damage and not after left. The loss of the negative. Well, right hemisphere, the idea is more not it's more connected to the lower parts of our brain. And the emotional state is how we relate to the world. It's much more fundamental, much more dealing with the primal connections. And so and we do see a left visual field advantage. That means the right hemisphere advantage for emotional recognition. So and the tones and all that things. That's expressive. So one thing about emotions, you got to feel like there's experience of emotions and there's recognition of emotions. And there is, what's the third one? Experience and recognition. And expression. No, but expression and experience are kind of the same. But all right, well, it is a little bit of a confusing picture. And the case being that you can argue that okay, that the left is more positive, and the right is more negative, but the right has more access. That's probably the consensus you get to. Well, we do 6 emotions, just 2 general emotions. The idea of dealing with how sensitive you are to reward and how sensitive you are to punishments, and that sensitivity can manifest in many ways. So if you're very sensitive to punishment, you can go out and more than to the reward, you get that anxiety, neurotic profile. If you're more sensitive to reward, you're more impulsive. If you're more sensitive to reward and not very sensitive to punishment at all, this is just a global reduction. That's the more extroverted profile. And the converse is the introverted profile, where you're more sensitive to punishment, so you hardly act out, hardly do anything. So we do have this the argument that the left is the positive, the approach, and the right is the negative and the withdrawal area. Area 46 in particular. Okay, other global right hemisphere, left hemisphere difference. Right hemisphere is the holistic, picks up the context. The left is the parts, and it picks up the local content. And you can see they do this one test of what's called global local task. And sometimes ask what's the letter made out of. That would be a local task. What is the letter, the larger letter? That's the global task. So you can have things like where it's inconsistent here. That's consistent. And you do see that the right hemisphere is showing, and then this is reaction time, so higher is worse. So when you're asking for the global, the right hemisphere is going to be faster. When you're asking for the local, the left hemisphere is going to be faster right there. And much easier to see that is in these damaged patients. Those who have, left hemisphere patient means that that's the hemisphere that's damaged. And then you can see that all they have is the right hemisphere. Primarily available. So when they try to duplicate this, they can just see, they don't see the parts, they just see the whole. The left hemisphere, the people have only a left hemisphere really intact, and right hemisphere is damaged. They just see the parts, they can't get the wholeness out of it all. You just see, they don't know how the parts relate, but they see the parts. Same thing over here, they see the parts, but they don't see the relationships. In the right hemisphere, people who have right hemisphere see the relationships, don't see the parts. Here's another example. Williams syndrome is a interesting disorder where the person is very involved in facial recognition, very social, mentally delayed. Down syndrome, you can see that that's an example, just like this one, where they are not seeing the parts, but they see the configuration. Yeah, they just see the configuration. They see the parts, not the configuration. Okay, did you see asymmetries in the hemispheres? Like, for instance, in the language, autism, most of us will use our left hemisphere to do a speech eventually in the right hemisphere, and perception and listening. We'll have some on this right side and more on the left, because we're going to parse here and figure out the tones here. And the autistic not using the proper brain parts in essence, and that makes the task much harder. You can see this is an fMRI. You can also see this is ERPs. The ERPs, you can normal subject first, you see the amount of cells is equal to that height. So in the left hemisphere is that higher one, the straight line, the solid line, and the dotted line is the right hemisphere. So you see also little differences going on there, and that's early discrimination. Well, there's no differences really, and until it's too late, and then there's not much height. I mean, not as many cells are responding, and that was probably over the auditory cortex, I assume. Okay, one of the things the right hemisphere gives us, though, it processes the world kind of like an idiot at some level, but it's a helpful idiot, because when you say a word, the right hemisphere brings up all its meanings. It brings up the entire lexicon for that word. The left hemisphere very quickly will bring them up, but collapse to what it thinks is the dominant understanding, and that's very helpful as well. And so they're really good partners. And for instance, if here's for example of when you have to revise what you hear because it doesn't follow the dominant meanings. Sally was became too bored to finish the history book. She had already spent 5 years writing it. So most people, when you hear this, you're bored to finish, will think of reading, but your brain, your right hemisphere maintains other meanings. Your left hemisphere very quickly collapsed to that. Oh, she's reading it, but here's even a better one. We saw her duck. What's that mean? One of these. Which one does it mean? Well, the right hemisphere brings up both of those. It was wearing a hat. She was almost got hit with a bat. So the right hemisphere generates extensive representational sets, and the left inhibits. It finds a dominant one for what it's reading, often the most dominant meaning, but it's contextual typically. So we'll find that it will get to collapse, and within 40 milliseconds, they've done studies on that, how quickly it will collapse. 40 milliseconds, the left has one meaning. I put my money in the bank so it wouldn't get wet when I crossed the river. You know, I meant the river bank there. But the right hemisphere, the moment I say bank, open up the turn idea, like a plane banking. It's done the river bank. It had the building, and that had all the meanings. Okay. So we need this dualistic language system to understand narrative, to do inference, metaphor, humor, indirect requests, such as, you know what time it is. That's a request to tell me the time, stuff like that. It's all handled by the right hemisphere. Figuring out theme, what's going on. We need the right hemisphere to organize. I'm not gonna go into this detailed here, but it just shows the right hemisphere is needed to organize the theme. And when you delay what's happening, the right hemisphere is really, if you have damage, it's lost. Okay, so think of it is how the hemisphere is developed is there's going to be an anatomical tendencies or anatomical precursors for this dualistic processing, but there is in the beginning more plasticity. In fact, if you have a loss of a hemisphere, as mentioned in that Wigan case, what we'll eventually see is that the left hemisphere functions will be more in the center, where they can be tightly timed, closer focal networks, and the right hemisphere function will be handled more on the periphery of the single remaining hemisphere. Now, someone who has a hemispherectomy, it happens rarely, they still don't have enough material to really get to abstract thought, and they'll still have delays their entire life. They just don't have enough cc's, don't have enough grams, the material to handle some of the more advanced thinking, just like the primates, the other primates. Even they have left and right hemisphere, but they only have a few hundred centimeters of each. They need more. So depending on what we're measuring, so they're 1/3 our value in terms of the neocortex, the chimps, for instance. But if the damage is early, there's more swapping, more plasticity available. But as time progresses, it's more of a problem. In fact, brain injury is more of a deficit in the person's life if it happens in their teen years than in the early years or adult years. It's in the teen years that greatest problems emerge. Okay, so I love this understanding, because this is a major thing of how we describe our brain thinking, what's going on in our process and our brain injuries and functional issues. And we find in neurotherapy is we start off as relational thinking everything's about us, and we can see this even in babies and so forth, how things are more thematic and associated and don't become categorical until we really start speaking a lot. In the left hemisphere, we start off relational, maintaining the details of everything. It looks like we almost have photographic memory in the beginning of life. But then as we start to learn language and speak, we start using this categorical representation, and we start losing that ability of perfectly remembering all the events. And that's why it's just more efficient. So we don't have to, when someone talks about a horse, we can go to the category horse, and we don't have to think of the instances. The reason why we know this is what's going on is there's a number of reasons, but one is like with savants who are still in that photographic memory
issue, or eidetic memory, it's called. So the we see in our own brain maps, those are what areas are still doing relational thinking or dominant in the relational thinking and not doing the object thinking where things are independent of us. Okay. In fact, language itself, what this is trying to show you here, is language itself is a cue to go categorical. So when not given, this is with really young kids, and they're given, okay, here they show an object like a little figurine, and they have other objects and say, what goes with cow? And the kid, when, see this, can you find another one? They'll choose milk. This is when there's no other cows there. All right, they choose milk. They choose the associative one. But you go, see this DAX? Can you find another DAX? That term, by putting a word on it, we go categorical. And now they choose the more categorical element. Okay. New word learning shifts children's attention from thematic or associative to categorical. This is a nice maps. And you can see they use a bunch of data there. And most of the time, the most interesting element, this is using over the lifespan, these various areas, and then male versus female. The linear ones are the ones that curve, that get this exuberance, and then they get a reduction. Those are cool ones, they make sense, but the more interesting ones are the ones that go up, because it means that being a grandparent, this area is needed for being a grandparent. That area is needed for being a grandparent. So this is, if this is truly near each other, which I think it is, this is your attention area. This is, well, imitations like right here. This visual complexity, OCD and social anxiety out there. This is long. This is your trust and suspicion. You have fewer cells there. You gotta get more trusting. What else is up here? That's probably 46. That's the approach withdrawal. Again, they're not even showing the two hemispheres, so there's a deficit right there in their thinking. UCLA, my alma mater, because the two hemispheres are not going to be identical like this, and to collapse them together, right? That's one thing that's frustrating when you do right and left hemisphere studies, is that often sometimes it's getting much better. It used to be they just collapse things. You just see one version, and sometimes you need to do that, collapse them, but if you're trying to show something that's very subtle, collapsing across the two hemispheres is not going to be helpful. Just duplicate the hemispheres and show us each hemisphere, or show the other pattern right beside it here. This is actually recruitability. See, there you go. Recruitability goes up. This is grandparent. You got to be more recruitable. Look at those ones right there. Those outliers there. Right there is recruitability function. This is your social boundaries. All these ones are these are the cool ones that go up, because that means they somehow were needed for grandparenting. Linear ones, those are kind of expected. And things like this that could curve up for a while, the exuberance. But you can see all that. Look at all that outline is a factor of 4 in some of these ones. Again, showing that sometimes the uniform, trying to find some universal principles is kind of false. That's why you want to do personalized brain mapping. I'm going to skip over some of these older ones. These are older slides I've had for a while. And okay, so when they do tests of what's the most reliable sex differences, men are good with usually visual spatial tasks, higher mathematics, not counting statistics, and physical aggression. Women are stronger in relationship aggression or relational aggression. In fact, there's one figure that added those two together, and men were less aggressive when those were added together. That the little physical aggression was small enough, and the relational was even smaller, and then when you add these two together, in fact, they're kind of like equal in these two levels of aggression. When the men more physical was equal to the amount of physical aggression was the same amount in women of relationship aggression, the relational aggression. And when you add a little bit of the other complementary one, each gender, men were slightly less aggressive than women, because relationship aggression was much stronger, keeping the, protecting one's young. Verbal tasks, women were better. You can see some of this in injury where the left hemisphere, this is interesting, where the left hemisphere lesions in women result in loss of the IQ in both verbal and nonverbal abilities, where it's the right hemisphere
lesions had less of an impact, where the men were more lateralized. This is just showing how men are more lateralized and women were less lateralized. That's probably one of the most reliable ones I keep seeing. But you can see in all these various skills, it goes back and forth. Men may be good at one thing, women at another thing. So it's very complementary, all complementary. In fact, in the brain, you can see what I call the masculine pathways and the feminine pathways. You have these ancient pathways, and then you have these newer pathways. And the ancient ones usually the female one, newer ones in the evolutionary terms of the male one. And the quicker to respond is the male, the female ones are slower to respond. Even in the brain, you can say like the astrocytes are female and the neurons, the pyramidal neurons are male. And if you type, when you were reading papers about astrocytes and neurons, and you just put in male and female, substitute those terms, and you'll see it usually works pretty well. Astrocytes being female, the slower ones, and in terms of response, and males respond too quickly. Okay. All right. Talking about how is the hemispheres organized by gender, and the most common one would probably be, see, the one I would like the most. Oh, all very confusing. I think it's this one. Verbal and nonverbal, very lateralized. Where the women have verbal, they have verbal on the other side as well, and nonverbal on that side. That one's probably the dominant one, but you can see there's other types of arguments. Hemispheric, women have greater callosal connectivity, meaning that there's more merging of the two hemispheres, or more inhibition. Typically, you have inhibition and transfer of information in the corpus callosum. Intrahemispheric, language organization differs by gender. Strategic, women employ the verbal strategies more often, even for spatial tasks. Mediated differences due to other traits such as handedness, familial, and cognitive style, maturation, hormonal. I had an individual in my lab who was studying the hormonal effects on hemispheric differences, and they did change in women over the month, over their menstrual cycle. Okay, I'm going to save that one for a lot of time. Okay, so the hemispheres deal with a way they sort of break these dichotomies up. I mentioned the analytical gestalt one. We were just looking at Levy a second ago. Bogan, propositional meaning versus sort of configurational. I like to use the two infinities. I think of some respect, either where probably we're a third infinity, or there may be many infinities, but we know two definite infinities. There's the countable one, 1, 2, 3, 4, 5, just keeps going. And the indefinite one, or the countable one, and you can represent the continuum by 2 raised to the infinite, which is actually bigger than infinity. The countable one, think of the integers. 2, what is adjacent to 2? 1 and 3. We know those are always adjacent if we're counting by infinite integers. But the indefinite one's best thought of as by like the decimal system. What's the adjacent to 2? Is it 2.0004? Is that the one next to it? And life is more like we live in the continuum, space-time continuum. We live in this higher infinity where we get new adjacents all the time. Someone walks into our life and and suddenly they're important and they weren't before. Our family might be the 1 and 3 if we're the 2, where we have this, we have what our past parents are always 1 and 3 is our children, but all the things in between, all those adjacents are can vary and wax and wane and so forth. And so that continuum is to understand life is the sort of thing, recognize that either we are the continuum or we're even a higher infinity that experiences the continuum in our perceptions. Luria, famous neuropsychologist from Russia, think of the left side is sequential, the other one simultaneous. Sam's looked at the anatomy of the brain, and left hemisphere being more focal, the networks more closely connected. They need to be closely connected for like phoneme detection, because phonemes can be very, very fast, and all the way down to like 8 milliseconds, and you need to be able to just the limits of the physical systems and speed of light and speed of electrical transmissions and electrical chemical connections is you need the focal network to handle those fast times. Focal versus diffuse, that's probably a very useful one as well. I Ching says secretive versus the receptive, what I was saying, expression versus the receptive, heaven versus earth, and the masculine versus feminine, yin yang, or yang yang. Yeah. Verbal versus spatial, intellectual versus intuitive, causal versus synchronicity, acausal, non-causal, argument versus experience. So on this side, we do the categorical. This one's the configuration. It's more of an open system, maintaining the details. This one's closing, collapsing to the category. All right, that is hemispheric differences. Have a good day. Bye-bye.